If you guys haven't been here for the past few weeks, few months actually, you might note that I've been incredibly spotty with streaming. That is to say, since basically January, my streams have been like maybe 2 to 3 streams a week at best. And even then, they've been really kind of lame streams where we haven't gotten anything done. The big reason for that is I've been working on a project known as the Fractal Animation Engine, Fei.jl. The Fractal Animation Engine has a clear goal of basically rendering objects without using meshes and instead using fractals, right? So let me talk about what that means. So when I say meshes, what do I mean by that? Well, if you're going to do something like ray tracing, right, you'll have some idea of maybe like a circle or something like this. But at the end of the day, this circle is probably represented by a bunch of, little triangles, right? So I guess I'll just draw some triangles here, something like this. This isn't always the case, but, for the most part, you have taken this particular object and you've turned it into a bunch of object primitives, right? This ability to mesh any object, the strategy to mesh any object, like for example, mesh a human face or something like that. Yeah, people can do this. They do this all the time. It's not like this is a huge engineering challenge. However, the problem comes that most people will draw the face first, right? So here's your little XD face or whatever, and then they get the primitive from that. So they draw the face, and then they use some sort of algorithm to auto-populate where all the triangular faces are, right? So primitive here. My issue was that I wanted everything to be analytical, right? I didn't want to have to draw something and then have that thing turn into something that my software could then render. I wanted just to be able to render everything directly from the math. So here's exactly how this works. So the Fractal Animation Engine, Fei.jl, works on something called an iterated function system, right? So we'll talk about that next. So an iterated function system is, IFS, is essentially a way for us to go through a function system and create some sort of object from it. So for this, let's go ahead and go to the algorithm archive here, and let's do iterated function systems here. So the classic example for iterated function systems is the Sierpinski triangle. The idea is that we have 3 points in space, A, B, and C, and we have 3 functions, P plus A over 2, P plus B over 2, and P plus C over 2. These effectively will take any point P and move it halfway towards A, B, or C. You can combine these guys all into one large function system called a Hutchinson operator, and for the sake of the argument, let's say we create 3 new points, D, E, and F, and we allow each of them to generate 3 children. One of each child, one child from each of the parents will move towards A, another child will move towards B, and another towards C, which will create some sort of visualization like this one here. So we get 3 new points to the left, 3 to the right, and 3 up. If we allow those children to generate children, and those children to generate children again, and again, and again, and again, you eventually will start to draw the Sierpinski triangle. The point of this is as long as we sample this set of function systems, as long as we are going through them in a kind of uniformly distributed way, we are able to draw the Sierpinski triangle. So for example, we can also draw it with something called a chaos game. The chaos game works by essentially starting at some random point in space and then picking a function at random, right? So we start with the point here in the center, and then it chooses, okay, I'm going to move half towards C, then towards A, then towards C again, then towards C again, then towards A, then we're going to move up towards B. And at some point, by randomly choosing functions back and forth again and again and again, you eventually find yourself on the Sierpinski triangle. Once you're on the triangle, and the question of being on the triangle is kind of vague here, right? But once you're sufficiently close to the triangle, you can't escape. You're always going to be on or sufficiently close to the triangle. In fact, this visualization of the triangle behind here was actually done with a single point that was moved, 10,000, maybe a million different times. So it was just one point being plotted over time after it had landed on the triangle to begin with. So another key takeaway here is that if you change the set of equations, for example, you do P plus D over 2, you also change the shape. So here we went from the Sierpinski triangle to just a square, right? And you can also do things like the Barnsley-Fern and stuff like this. We've talked about all of that before. So the key problem in drawing a circle as a fractal is that, it isn't exactly obvious how it's self-similar, right? And so let me try to describe this in a bit of a different way. So what we're looking for is we're looking for some sort of domain that attracts all of our points to it. And we want that domain to be a circle, right? So what we're looking for at the end of the day is essentially a circle that is shaded in this region in here. So we want this entire region here to be all constantly shaded, right? Right. And if we want it all constantly shaded, then what we're looking for is essentially a uniform, random distribution but only inside the circle, right? So while this square up here was a uniform random distribution between A, B, C, and D, we want one that is just basically around this circle. So how do we do that? Well, one way is to pick some point R, right? It doesn't matter, some point P, right? This point P, we're going to say, is in circular coordinates, so it's going to have some sort of radius and some sort of theta. And all we're going to do is we're going to say, okay, our new radius, which I'll call R prime, is going to have to be somewhere between 0 and 1. We're just going to assume this is a unit circle, and then we can, kind of make it bigger or smaller depending on how large we want the radius to be. So some way in order for us to get a value between 0 and 1 would be to take our theta value and divide it by 2 pi, right? So what this does is it kind of allows us to always find a value between 0 and 1 for our new radius. Now our theta value here can also be somewhat related to r. So we can say this is going to be r plus, and I'm just going to put another value here called j pi, right? And so the idea here is that we can essentially like simulate that uniform randomness, simulate that idea of being random inside a circle by basically flip-flopping these coordinates. So we use theta to calculate r and r to calculate theta, right? And by doing it this way, we've essentially simulated that randomness that we need for that uniform random distribution inside of the circle. But there's one key thing here that I'm missing out, and that's this parameter j. So like I said, r can range from 0 to 1. J is going to be either 0 or 1. It's not anywhere in between. It is either 0 or 1. So the idea here is that we have two sets of functions. One set of functions where j is 0, and another set of functions where j is 1. And this allows us to split the circle in half. So we have a top half and a bottom half, right? And so one function will allow us to uniformly generate that top half, and the other one will allow us to uniformly generate that bottom half. And this allows us to essentially create a mostly random situation that will give us a uniform random density. Let me go ahead and generate it for you then. So we're going to cd into projects fractal animation engine. So those equations that I showed you just a second ago will actually not generate a perfect circle, and I'll show you why right now. Okay, so now let's go ahead and take a look at the image that we just generated. Check.png. So what just happened here is we generated a circle via the equations I just showed you, but the center of the circle is very, very high in density, whereas the outer points of the circle are not very high. And you might be thinking to yourself, okay, well, why is that the case? That doesn't make very much sense. After all, like, didn't you just say, like, all these equations I just gave you were to generate a uniform random distribution inside the circle? The answer is yes. The equations I gave you do generate a uniform distribution, but what it does is it generates a uniform distribution along r, and then a uniform distribution along theta. The problem with that is that if you have a uniform distribution of points along r, and then you kind of spin those along theta, well, let's say you have maybe 10 points around a small circle here, and 10 points around a slightly larger circle, and 10 points along a larger circle over here. Well, that clearly means that we're going to have a higher density here because the radius of this particular circle is smaller. In fact, the radius of every circle is always going to increase as pi r squared. So we can naively say that the density of points, the density function for points along the r value should probably scale as square root of r. And if we scale things as square root of r instead, let me just go ahead and show you guys that one right now, then everything actually works out perfectly fine. This particular set of equations that I just showed you were not actually found online anywhere. I found like a paper that I was trying to go through maybe at the start of this month, actually maybe a month ago from now, that had like 9 different equations instead of the 2 that I showed you right there. And frankly, I could not get it to work. Then I found a random website that gave 2 equations, but the 2 equations that it gave us the wrong answer. Essentially, it gave us the non-constant disk, right? Whereas we wanted a constant disk, right? So the question is, how do we go from the non-constant disk to the constant disk? The website that I found also gave us something to give us a constant disk, but I couldn't get that to work in this particular code base. Basically, there were a whole bunch of issues just getting the equations to work. But the bulk of the challenge of this particular project was not in finding the equations. It was not in, figuring out like what a fractal circle looks like. It was actually in getting this to run in parallel on the CPU and GPU and allowing people to actually write whatever equation they want and have that immediately solved on the GPU, right? So people can write whatever function system they want and we can solve it for them, and we don't have any problems with that. There were a huge number of hiccups that happened in that process. The creation of different histograms Like I said before, this is essentially a histogram, right? And so the creation of histograms itself was not possible to do with kernel abstractions, which is a library that we were using at the time in order to write the CUDA code and to write the CPU code, because it didn't have atomic support. There was just a bunch of things like this that we had to do. So it took like a few weeks to get kernel abstractions to work. Then it took a few weeks to figure out the symbolic logic. Then it took a few weeks to figure out the circle stuff. Then it took a few weeks to do this and that. And when you put it all together, it's been like 3 months of me just trying to draw a circle. That's it. Now you might be asking, okay, well, if you could already draw a square, why do we care about circles at all? And the answer is because this process, the entire purpose of this project, is so that we can do meshless rendering, right? Rendering without having to deal with like object primitives as much, right? And the idea here is that we need to find ways in order to kind of think about how we might draw an equation for particular shapes, right? So like circles are obviously essential for like drawing like basically any system, right? And so the hope was that if we mess around with the system a lot and we learn how to draw circles and squares and triangles and stuff like that, we can eventually start using this for more complicated shapes and stuff like that. At the end of the day, we're probably going to have to use machine learning or optimal control to basically give it some sort of image and have the algorithm learn what that image is supposed to look like via a set of equations. But yeah, at this stage, we are finally able to draw a circle, and that took quite a long time. Maybe I missed, but can you show the circle fractal zoomed in? Does it look like any different than a normal circle? Yeah, let's take a look at that actually, because I am being stupid. So here's the fractal circle. Now, there is one problem with the fractal circle. A couple problems. So one, if you do zoom in, you do notice that it is not quite as smooth as it could be. I need to put a SOPA filter in there.